If any speaker tells you ever that they're not nervous, they're probably lying, and I'm really always super nervous at the beginning of my talk, so I try to kind of offload some of the nervousness to you. There is a thing among speakers that good talks start with audience participation. I don't really like it when I'm in the audience, so I won't put you through this, but just in case, how many people have been to a talk that started with a raise of hands? Thanks, thought so. I'm Piotr. I'm kind of technically officially Polish, but my mother was born in Silesia, and my paternal great-grandfather was also born in Silesia. That puts like over half of my genes, a little bit over, on the Silesian side. And my mother is from Ząbkowice Śląskie, which is a Silesian city that, if you're into European history, probably know that wasn't called this way before the Second World War. And it's been Ząbkowice Śląskie for the last 70 years, but for the previous 700 years, it had a different name. It was a city that was created at the crossroads between Wrocław, so Breslau, and Prague on one hand, and Świdnic, which is Świdnica now, and Nysa, which is Nysa now, on the other. And there were 3 attempts to locate a city at the crossroads, because it was a crossroads of major trade routes. And the first one was Frankenberg, and that didn't work out. They tried to do another city. It was called Levenstein. That also didn't work out, and I thought that maybe coming up with new names is not necessarily the good idea. So the third city that they located there, they decided to call after those 2 cities Frankenstein. So Frankenberg on one hand, Levenstein on the other. And this is Schloss Frankenstein. It's the castle in Ząbkowice Śląskie, obviously. And it's not the same castle where the Mary Shelley's Frankenstein was happening, because that's in Darmstadt in Hessen. But I thought it's a super cool name that my mother comes from, Frankenstein, even if she was a little bit late to this city be called that way. I want to talk about Frankenstein programming, which is seamlessly combining more than one language, and I show you how to combine 2 and, with a little squinting of our eyes, 3 languages together in one even file, and see how it goes. There is this meme about Frankenstein not being the name of the monster, but rather the doctor who created him. Like, common misconception, Big Ben is actually the name of the clock's creator. Its correct name is Big Ben's monster. If you don't like this meme, I'm happy to report that my talk will be over in 30 minutes. So, benchmarks. There will be a lot of benchmarks, and I want to give you a huge caveat about benchmarks. A wonderful quote from Eleanor McHugh, and she said, "Synthetic benchmarks tell sweet Fanny Adams about real-world performance of code, architecture being a much more significant consideration than the proportion of raw MIPS a given language will deliver on a given platform. The average netbook could happily run all of Teller's fusion bomb models, along with a full telemetry analysis of all of the Apollo missions in the pauses between loading XKCD comics and binning junk mail without the user being any the wiser." Don't try to fix your applications by rewriting them one-to-one in another language. Don't try to think that, I'm pretty sure this is the bottleneck, so I'll just rewrite it. Always try to fix your architecture first, and then try to benchmark and see actually where things go. But don't fall for the synthetic benchmark, like small benchmarks that show that this language is faster than the other one. Don't fall for this. It's usually people have at least a sentiment to want more of the languages that they're benchmarking, so it shows more or less. I want to show this on a simple example. There are a lot of people who say that you shouldn't do control flow with exceptions, and there are good arguments for this. There are bad arguments for this, and one of the worst is that exceptions in Ruby are slow. So let's see how slow they are actually. I would assume a small active record, so Rails application, that connects to a local database. So it's as fast as it can be, assuming there is some kind of database behind it. And it works on local hosts, so there's no network latency. We create a simple table whatevers with a one text column. You can't go any simpler. And we migrate the database up and down when the script finishes. And then we compare how much it takes for exception miss, so a code path that doesn't hit the exception hit, a code path that actually raises something. We rescue it because we need to don't want our benchmark suite to blow up. And then we do the simplest select, which in the case of active record is just a first row. And then we do a simple insert. Also, the simplest table, no indices, so there's no index overhead and so on. And when we run it, we see that, yeah, exceptions is super fast and exceptions are super slow. They're 10 times slower. But a simple select is 300 times slower still than an exception hit. And an insert is almost 7,000 times slower than raising an exception. So don't fall for people who say like exceptions are slow. Make them show you benchmarks. If we have data, let's look at data. If all we have are opinions, let's go with mine. I love this quote because I use it all the time at the office. Please, always benchmark. First, adjust your algorithm. There is a urban legend / common idea that you can make your algorithm, your implementation, your bottleneck 10 times faster just by adjusting algorithm. It's not universal, but it's surprisingly often the case. It's surprisingly often you can rewrite something and see that it runs actually an order of magnitude faster, and we'll see it in a minute. And also consider whether there maybe are alternative implementation for your language. So if you run on Ruby, there's JRuby, there is a truthful Ruby coming up, there've been in the past other implementations, and the same, there's a Jython for Python and so on and so forth. But if you did all this, and it's still too slow, it might be worthwhile to look into other languages. There is this kind of tweets like, oh, it's awesome, Crystal is awesome, we can have 1 million requests per second on a single server. Always look at what they are benchmarking, because I don't know what happens here. There is no link to the benchmark. If I were malicious, I could say that maybe it's just a empty file, and what you should benchmark against is just Apache serving a directory. And maybe that's what it's actually happening here. So always verify what people are actually benchmarking. Pivotal is the company that created the story tracking software. The actual name of the software is Pivotal Monsters. I actually grew much more fonder towards Pivotal after working with it for half a year, maybe. Stockholm Syndrome, maybe something else. Anyway, let's talk about binary representation. Let's say we have a set of elements, for example, integers, and we want to do things with sets of integers. This is not a made-up requirement. It's not something that I only used in my PhD because I actually was working on sets of elements. This is actually a use case from a startup that was delivering food to offices, and they had an arrays of integers which denoted which offices have which food allergies and which menus trigger which food allergies, or actually don't trigger them, maybe. So let's represent them by setting a bit on a single integer. So rather than having a large set, an array, or much better, a set, actual set of integers, let's have one huge integer with certain bits being set to 1. So for example, if you have a set of 0, 2, 3, and 5, you can have an integer where the 0th, 2nd, 3rd, and 5th bits are set. And then you can do set operations as binary operations. So if you have those two sets and you want to find their intersection, you can do this binary operation of just ending or intersecting those two integers, and this operation in any decent language should be one processor operation. It's probably not in Ruby, obviously, but in a decent language that actually knows how to compile things. So that way you get a different integer with this particular bit notation, and you can kind of interpret it back as a set of 2 and 3, which actually is the intersection. But what I want to talk about is the size of those sets. If you want to have a size of the set, you need to do something that is called population count. So the number of ones that are set in the binary representation. If you have number 6, then 110 is the binary representation. There are 2 ones in that. So for this set, the pop count will be 4. For this one will be 3. For this one will be 2. So this is the number of elements in our set without leaving the binary representation, without having to count those elements at all, provided we have this method. So let's try to implement it in Ruby. In Ruby, you can reopen classes, including like core classes, like integer. Aaron Patterson called this freedom patching. So let's freedom patch integer. Let's add an instance method that is called popCount2s. And let's implement it like super naively. Let's use the 2s method that turns an integer into a string. But if you pass it a number, it will turn it into a string of the given base. So a binary representation is 2s with the 2 as the base of the conversion. And then let's count the number of 1 substrings, so substrings with the character 1 in them. If you're internally squinting now and in general disgusted by this implementation, I want to defend that it's super simple and super readable, probably. But also you might think that obviously there are faster implementations. Like obviously you can just try to shift the number right 1 bit at a time, and then increase the counter by either 0 or 1, depending on what's the last bit. And this is basically what it does. If you have the number like 110, which is 6, then that loop would fire 3 times, 1 for each of those bits. So this will only happen as many times as there are bits in the most, like in the shortest representation, binary representation of your number. So this obviously should be so much faster than going to a string and counting substrings in it. There's also this implementation. You don't need to kind of figure out how it works. The gist is that it only loops the number of times it loops is the number of ones in your string. So if your string, if your number is 1 and 27 zeros, this loop will only fire once, where the previous one will fire 28 times. And then there's this implementation, which is absolutely lovely. And you could think these are some random numbers that people just dreamt up. But first, it actually works. Second, those numbers are not really random. Like the 5555 in hex are 01010101 in binary. The 3s are 0011, and so on and so forth. So this implementation does some masking and then some calculations that are maybe faster, maybe not. We'll see in a second. But then you could think like there are actually languages that have this stuff implemented. There's Rust, which implements, it has built-in method that is called count_ones that you can call on any integer, and it will give you the number of ones in that integer, so the population count. And thanks to the wonderful Helix project, you can use Rust code from your Ruby application without having to do almost any work. This is a Rust file that just gets compiled by Helix, and Helix then hooks it up to your Ruby in a way that you can call popcount.count and pass it the number, and you get a Ruby number back. Super useful. Hopefully this will be fast. It goes through a compile language that counts the ones. But we can go even deeper. We don't have to leave Ruby. There's a Ruby inline gem that lets you write C in your Ruby code. You write it in a string, and when this code is loaded, this is like class level code, so it executes the moment you load this file, and this C code is compiled, and then the Ruby code hooks into it, creating a function that is named exactly as the C function that this code exposes. So this gives you an instance method popcount_bit_lmc into any integer in your code that's actually written in C, and that's also the bit elimination approach. But if you have a laptop with a processor that is newer than November 2008, which you probably have, then you have Nehalem or later architecture. Nehalem was the one before Sandy Bridge. And ever since that architecture, there's an SSE 4.2 support in those processors, which means there is a direct assembly code that executes directly on that, like in one cycle, that counts the ones. And in decent C compilers, you have exposed this kind of things. In this case, in GCC, it's __ built-in _ popcount_l. So this code is in pure Ruby on the first look of it. The moment it's executed, the C in that string is compiled, and the compiler knows to compile this line into a single instruction if your processor supports it. This might be fast. Let's see. But as I was saying, not everything needs to be written in a different language to be made faster. If we pre-count all of the population counts for numbers from 0 to 65,000, and this takes less than a second, then we can just, slice our number into 4 parts. We are like softly assuming from some point on that we are doing 64-bit numbers. We can slice our number into 4 parts, like mask them out and look into this cache and just add this. Like we have pre-computed all of the pop counts for, any 16-bit number. Let's see how fast this is. And we can benchmark it very nicely. The benchmark IPS gem does the kind of benchmarking we saw already, but Ruby also, you can call an instant methods method on a class, and it gives you all the instant methods as an array. And then you can grab all of the methods that starts with popcount underscore from that array of methods. So now we have an array of method names that start with popcount. We do like a soft check whether all of our popcount methods return actually the same numbers for that random array of 1064-bit or 62-bit in this case integers. And then we basically loop through the methods and map the numbers from the array over the given method. So we can actually compare how this works. And if we run it on Ruby 2.4, we see that the built-in one, the one that compiles a C code that should compile to a single instruction, can run like 30,000 times a second. Then the other implementation in C runs 70,000 times a second. But the next one, the first pure Ruby one, is actually comes up at 5,000 times a second. It's not that slow. Interestingly, the Rust one is slower and significantly slower than that. Always benchmark. The 2S one is only 5 times slower than the cached one. So going through a string and counting substrings in it is actually only 5 times slower than doing the pre-caching. And surprisingly, maybe to a lot of you, if it was to me, it's actually faster and significantly faster than the bit manipulations one in Ruby. So the reason is that in CRuby, the 2S method is actually implemented in C. The count substring one method is also implemented in C. So this is why it's faster than the bit elimination and the continuous shifting methods. But there are other Ruby implementations. In JRuby, those numbers look interesting. The cached one is slowly faster. The proc shift one is significantly faster. Bit elimination is significantly faster, like twice as fast almost. The 2S one is actually slower. Continuous shifting is, again, over twice as fast. But JRuby runs on JVM, and JVM kind of sometimes needs a bit of time to warm up. And also, JRuby by default uses some of the invoke dynamic mechanism introduces in Java 7, but we can actually force it to use more of them. So we can give JRuby a longer warm-up and force it to use as much invoke dynamic as it can, and those numbers differ. The nice thing about benchmark IPS gem is that it tracks standard deviation. So it can actually tell you that cached is slower than proc shift, but the difference is smaller than the standard deviation that you had. So they are actually same-ish. And this is actual output from the benchmark IPS gem, for which I'm super grateful, because no longer somebody comes to you and tells you like, my algorithm that has 3 pages runs 2% faster than your one-liner, and even though the standard deviation is like 10%. So as you can see, the numbers differ. The 2S number doesn't much. So again, not only benchmark, but actually know what you're benchmarking. Like, don't benchmark JRuby on a kind of not warmed up JVM, because the numbers might be different. We'll see whether they're always different later. This looks like Ruby, but it's not. It's in Crystal. And Crystal is a compiled language that has actual static typing. It just is very good at inferring the types. So the lines inside of this struct are down to every single letter exactly the same code as in the Ruby example. This is like byte by byte and letter by letter exactly the same code as in Ruby, except we reopen the instruct rather than reopening the integer class. And we don't have this kind of dynamic forgot the word, the dynamic introspection that you have in Ruby. So we could do that with a macro, but that would be an overhead, so I just spelled out the methods that we want to call here. But also, Crystal gives you a popcount method that has no suffix, so it's like natural, non-implemented by us, popcount method on integer. And huge warning, Ruby times include Ruby side call overhead, and I'll talk about it in a second. But just to remind you, these are the numbers from Ruby 2.4 with Rust, C, and assembly through C, and so on. And these are the Crystal times. So, sometimes you can get exactly the same code, compile it with a different, with a compiler for a different language, and you get very different numbers. And this is, of course, a very unfair way of putting this, but I just really like Crystal. So, as I was saying, never trust people who like one of the languages they're talking about. I also really like Ruby, and Rust. I don't like. Well, I like C to some extent. Again, always benchmark, and a huge caveat at the top. The crystal times are just by compiling crystal. There are not calls made from Ruby to crystal, because there's a overhead in dynamic languages, and it's not that the Rust implementation is slower than the crystal one, it's just there's an overhead in calling the Rust code from Ruby. So this is not a fair comparison, but at the same time, crystal is very similar to Ruby. So you might be, and you probably should be tempted to maybe not necessarily implement part of your Ruby code in Crystal, but rather factor out a microservice and have a pure Crystal microservice, which is fast, and just make it communicate with Ruby like outside of the Ruby code somehow. Cookie is the name of the scientist who created them. It's Cookies Monster, not Cookie Monster. Read the book sometime. When we cross between different languages, we have to figure out how to pass things. The best way is not passing anything. So have one language writes something to the database, the other language reads it from the database, does some computation, writes it back to the database, and then this way you don't have to pass anything between those two languages. The next simplest one is Booleans. Usually the Booleans are implemented in some simple way in both languages, so you can pass them and convert them on the fly in a way that is not really problematic. With numbers, we start getting issues because, for example, in Ruby, you have integers that are, they used to be divided into fixed nums, which are immediate, and big nums, which are, any large integer. And in Ruby 2.4, they were combined into a single integer class, so you can't really even, you can down to backward compatibility, but you get a warning that you shouldn't be checking whether a number is a fixed number or a big num. And passing bigger numbers than in Ruby's case 2 to the power of 62 is actually different than passing smaller numbers because the representation is different, not to mention of big decimals. Strings. If you pass a string from Ruby to C, you actually have to know whether the string is longer than 23 bytes, because strings in Ruby are represented in two different ways. Short strings are embedded in a kind of 40-byte Ruby object because there's about 23 bytes unused. So they are just shorter strings are put in those objects. Longer strings are put on the heap and just there's a pointer to them. So if you pass strings between Ruby and C, the macros are written for you, but if you're writing your own binary language, then you have to know that there are two kinds of strings in Ruby. And actually, the shorter ones are, there used to be 2 times slower. Now they're, the shorter one, okay, the shorter ones used to be 2 times faster. Now they're 50% faster than the longer ones. Arrays. In other languages, in some languages, in most languages, you have arrays of one single type. You have arrays of strings or arrays of integers. In Ruby, you can have arrays of anything, including the array you're talking about. The third element of your array can be array itself, and the ERB actually has support for it. It writes 3 dots in a square brackets, which basically I can't render it because it would be infinite loop of renderings. But you can put an array into itself in Ruby, and how can you convert it into an array of anything in C? And in hashes, it's even better because the keys can be anything, including a hash can be a key in itself. So, how do you pass a hash where some of the keys are strings, some of the keys are database objects, and some other keys are the hashes itself? And the biggest problem is passing structs and objects, which can have fields or properties or instance variables, however you call them, that are very different types. So let's do a second and last experiment. Let's do a code that you probably all use to some point if you do any kind of web application, which is escaping entities, so making text HTML safe, which is basically replacing the symbols on the left with the entities on the right. Right? So we need some way of taking a string and replacing the lower than sign or character with the ampersand LT semicolon thingy. And you might think that, okay, the pop count was maybe contrived a bit. I assure you it wasn't, but this is actually, I think, something to a lot of people can relate. We can do it very naively, as we will see. We can have an entities hash that basically has those transformations, and then we have escape each car string. We freedom patching string, obviously, because we can. And then we take an empty string, and for every car in our string, we push into the result either what's in the entities hash, and the fetch method takes another argument, which is a fallback. So if it's a double quotes, it will put the entity, and if it's the letter A, it will just fall back to the second argument, which will be, in this case, the letter A. But a lot of people don't know this, but a lot of people probably should know this. The gsoup method on strings in Ruby actually can take not only a regular expression and some string, but also a regular expression and a hash, and then the things that match the regular expression will be looked up in this hash. So you can do something like this. Pass a regular expression that will match on the keys of the hash, and then the hash as the replacement. And finally, hopefully, many more of Ruby developers know that Ruby actually has a built-in escape mechanism for HTML entities. You require CGI, and then you call CGI escape HTML self. So, but again, we can go to Rust, which is like super fast, and also has this thing that is called zero cost abstraction. So no matter how bad your Rust is, your compiler will actually make it so much faster because it will know how it should have been written. And I'm actually teasing. I absolutely love Rust, and this is not a case of zero cost abstraction, as we will see in a second. But let's do it like super functional in Rust. Let's take the input, take the cars iterator, and map over it, doing pattern matching on every single character and turning into a string, either a relevant entity string or turning the underscore one means the default one, the one that didn't match all the previous ones. So, for example, the character A, we turn it into a string, we get a collection of strings, and the collect method combines them back into a single string. So this should be, if the zero-cost abstractions worked how a lot of people think this works, exactly has this one, which basically let's create a mutating string, and let's start with a capacity of twice the input length, just because we know it will be at least as long as the input, so let's conservatively just add another input length into this, and then for every character, either push into this string an str, which is like literal Rust string that gets very nicely compiled into a string that is in your binary, and then it's referenced into like memory of your, like not actual program memory, but into your binary. Or just push this character if it's none of those entities. And then we return the result. When we run it, it turns out the Rust push one is actually the fastest, but the next slower is the CGI, the pure Ruby CGI escape HTML one. The gsoup is significantly slower, but the Rust map is slower still. And then the each car on the Ruby side. And the reason for this is because that's a very unfair way of saying about zero-cost abstractions in Rust. This is not a case of Rust zero-cost abstraction. So again, don't overinterpret things that you hear about other languages. Just make sure you understand what zero-cost abstractions are. In JRuby, this is actually slower. If you warm up JRuby, some of these are faster, significantly faster even, but some of those are actually not faster. So again, it's not always like this that you warm up JRuby and you suddenly get a faster code. And also the CGI, the pure Ruby one, so like the one at the bottom here, this is so fast because again, it's written in C and it's just compiled when you install Ruby. So meanwhile, Crystal, we can do this. The gsoup in Crystal can just take a hash, and Crystal just knows that if there's no regular expression, then you want to replace the keys of the hash. Or you can actually go into the Crystal standard library and call the HTML escape method, which obviously should be faster than the gsoup one, right? You know where this is going. But you can also read a little bit about that method, and it turns out there's another method that takes an IO stream and takes a string, and then it escapes the string into that IO stream. So you can do this. You can create an in-memory IO stream, pass it into HTML escape, and then you have to like turn this memory stream back into a string. Like obviously those last two should be exactly the same, because obviously the way you would implement HTML escape with just a string in those 3 lines, right? Well, no. The HTML one is the last one, and it's 70% slower than the IO one. The gsoup is actually somewhere between them, and like obviously, as any decent person who watches this, I created a pull request that re-implements HTML escape into the IO one. And just to compare it with Ruby, this is actually significantly slower than the Ruby implementation. So don't also think that, Crystal is so fast, so obviously its HTML escape will be so much faster than my CGI escape HTML. No, it's actually 2 times slower, right? It's half as fast. So don't fall for this kind of easy thoughts that If I implement it in a different language, it has to be slower. It has to be faster because the language is obviously faster. Always benchmark. There is a wonderful article called Optimizing String Processing in Rust, where our Rust push implementation, that is the fastest that we wrote, is actually the opening, and it says, let's take a very naive implementation of this and see what we can do about the speed of it. And the author speeds it up 5 times. So, you can make it run in sub microsecond times. And just do it in Rust and do some very bad things in Rust. I highly recommend reading this. The slides are online. The link will be at the end, so you'll be able to click that. So why does Crystal's HTML escape is slower? The way it works, there's a hash of the entities, and it actually escapes many more entities than the 5 that we used. And the self-escape with a string, so HTML escape with a string, just calls a gsub with that hash on the string, whereas the escape with string and IO goes through every character and fetches this into a stream, and then it doesn't return anything useful because it actually modifies the IO. And the reasons are a little bit more subtle, because the gsub uses string builder, which should be as fast as IO memory, but really isn't, and this is where it lies. But again, always benchmark. And yep, also when you're explaining the theory of relativity to physics students, you can say, no, Einstein is the name of his creator. I mean, Einstein's monster. It will be over soon, promise. So the last thing, and very briefly, that I want to talk about is whether this actually happens. Like, does anybody do this at all? Actually, the JSON gem, which is super popular, and if you do any web stuff in Ruby, implements JSON in 3 ways. There's a JSON pure implementation that is in Ruby. There's a JSON X implementation that is in C, and there's a JSON X implementation that is in Java. And if you're installing it on CRuby, it will try to compile the C one. On JRuby, it will try to compile the Java one. And if it can compile, or it's neither of those, it will just use the pure one totally transparently. This approach is being used as we speak, probably to serve this presentation. Levenstein gem, which is my absolute favorite gem that didn't get updated for the last 5 years, so it's also perfect by definition. It gives you the Levenstein distance between 2 strings, which is how many edits, how many deletes, inserts, and changes you have to do to turn one string into another. And again, it has this wonderful transparent fallback that if it can use a C implementation, it's super fast. If it cannot, it still works. It's just in Ruby. And the other magic thing about this gem, it works not only on strings, but it actually can take 2 arrays and tell you how many edits you have to do between them. And it can actually take any 2 objects that implement each, and where each gives you an object that implements hash and equal. So it can give you a Levenstein distance between whatever your objects are, provided the elements implement hash and equal, and the collections implement each. It's really, really cool gem, very small. I highly recommend that you watch it. And finally, the fast blank one, which gives you information where a string is blank, so empty or only white space characters. And the pure Ruby one works pretty fast. There is a re-implementation in C, and then there is a re-implementation in Ruby that works a little bit differently, and it's in surprisingly many cases like 17% slower than the C one. If you go into the fast blank repository, you have a benchmark that you can run and see in which cases which one is faster. I won't pronounce it out of respect to the people who mispronounce it all the time. But, well, we're in France, so who knows how you pronounce it here. Anyway, to wrap it up, your plans for after this talk and after this wonderful conference, please always benchmark, try to change your algorithm, see whether there are different implementations of your language, and only after try to combine languages together. Readability usually trumps performance to, it always depends. But if you say that your algorithm is 2% faster and it takes, again, 3 screens in comparison to one-liner, make sure your whole team is on board with this, because it's them who will be maintaining that code. And dynamic languages has a method call overhead that you should remember about. So maybe if you're trying to do this in a compiled language, think whether you don't want to extract this into a microservice. Read the source. Both Rust and Crystal are self-hosted, which means the compilers are written in Rust and Crystal. So it's not like, if you want to contribute to Ruby, you have to either know Ruby and C or Ruby and Java. If you want to contribute to Crystal, you just need to know Crystal. If you want to contribute to Rust, you just need to know Rust. And again, the sources are usually quite readable, so do it. Never create Ruby strings longer than 23 characters, obviously. This is a wonderful article by Pat Shaughnessy, and I highly recommend you read it. There is a wonderful article by Luca Guidi from the Hanami project about writing Rust gems with Rust and Helix. You can write Ruby extensions with Crystal with the huge caveat that you should really consider just writing Crystal. And if you're a Go person, then you can just write Ruby extensions in Go, and this will also work. So that's the last one. Actually, Frankenstein was the name of the scientist. I, the person correcting you on this trivial point, I'm the monster. Thank you so much. The slides are online. I'm from Rebased. We are super happy to be able to help a little bit with PolyConf this year. We have cute stickers if you want. You can find me, try to ask a question and get a sticker, or not ask a question and get a sticker. And thanks so much. The slides are up there.